Okay, so now we get into actual multivariable calculus. Certainly what you saw on Friday is of importance, but now it starts to really look like calculus. So this is 1.4 in the note in my notes. That is probably section chapter 13 in the textbook. So let's see how birthdays went. Although it's too bad they're not sorted. Okay. I guess what I do is kind of similar to what they call in statistics a stem and leaf plot, where I'm grouping everything by months. A lot of people have birthdays in September. Interesting. Okay. Because I taught a statistics workshop where we had 38 people, and there are actually 2 pairs of people that had the same birthday, and there were 2 New Year's babies, interestingly. Okay. Nope, no duplicates. Yeah, but again, it's only in this case a slightly more than 50% chance, so there's still a significant chance that it wouldn't happen. So, oh well. Okay.
Was there any that were close?
Let's see. If you're talking like within a day or two, the closest is like, for instance, we have 2 birthdays on September 2nd and 4th. That's the closest. So, yeah, like when I go out of state and play the lottery, if there's a way to get the numbers as wrong as possible, as far away from the winning numbers, that's what I do. So this kind of reminded me of that. Although I did win $60 once. So, all right, so I'm going to throw up a definition that you would have known from Calculus 1. Or let's see if you guys know it. So if I have a function of, so we're going to go back and forth between single variable land and multivariable land. Okay, so if I have a function of single variable f, and I'm taking its derivative with respect to x, and I'm evaluating its derivative at a certain point x naught. So this is one way to write it. Of course, you also know, or should know, the other more common way to write it, f prime at x naught. I don't suppose anyone would happen to know what the definition of that is from Cal 1. How do we actually define a derivative?
Is that the,
What?
like the slope?
Well, that's the interpretation of it, but the actual definition.
Tangent line?
Limit, okay.
Or tangent line?
Limit as, there's different ways of writing it, but I'll take any one.
X goes to 0,
Um,
approaches 0.
Oh, okay, so, yeah. All right, so they use h as our spacing here. Too rusty? Yes. Yeah, just put it out there. Moves class along, right? Even if it's wrong. Okay. Minus what? Fx naught divided by, this is a slope, as someone said, h, yes. So change in y over change in x, but the change in x is going to 0. Okay. And recall what that means, that this is the slope of a tangent line. Okay. to a graph of f of x at x naught. Also, some additional interpretation. Suppose we computed this derivative at a certain point, x naught, and we found it to be positive. What does a positive derivative mean? The function is increasing at that point. Okay, and then if it's negative, then it'd be decreasing. If it's 0, then you have a horizontal tangent. Okay, so I'm going to do the simplest generalization we can have for going to multivariable land. So this is for y equals f of x. Now, and technically this course is about functions of any number of variables, so most of the time it'll be functions of 2 variables or 3. So we'll look at z equals f of xy. So I can define using this symbol that is not a 2, partial derivative of f with respect to x, and we're evaluating at a particular point in the xy plane, x naught, y naught. Now, I mentioned this before, and I'll have to keep saying it again because I don't want to see this like on a test or anything.
That is not a 2.
There's no prime. Yeah, besides that, that's a good point. Also, prime is useless in multivariable calculus because when you only have the option of taking a derivative with respect to a single variable, like x in this case, then prime has meaning. But if you have multiple choices, then a prime would be ambiguous. But there is another way, shorthand, for writing partial derivatives, and it's important that you get used to this. So it's your function, and then whatever variable you're differentiating with respect to, because now that takes more significance in this setting, is a subscript. So f sub x means the same thing as partial derivative of f with respect to x, evaluated at x naught, y naught. So this whole thing refers to the partial derivative of f with respect to x. And I can define that as a limit in similar ways to what was done in the single variable case. So that is, again, the limit as h goes to 0. But I'm only interested in what's happening as x changes. So I have f of x naught plus h, y naught, minus f of x naught, y naught. So notice the y values remain fixed. So y is being held constant. X is changing because I care about what's happening to this function as only as x changes, and we still divide by h. Okay. So what we can say is, if the partial derivative with respect to x at a certain point is positive, then f is increasing as a function of x. So in other words, as you move away from point x naught, y naught in the x direction, so in my xy plane, here's my point, x naught, y naught. So if I move away from this point in this direction, along here we can say that f is increasing. But that says nothing about what happens if I move away from this point in a different direction, only in the x direction. So this is why we call it a partial derivative. It only gives us part of a picture as to how f is changing at a certain point. Whereas in a single variable case, we compute this one derivative, and it tells us all we need to know. So having an extra dimension, you need more than one number to get the picture, literally. Now, to get the rest of the picture, we need to take partial derivatives with respect to any other independent variables we have. So I can take partial of f with respect to y, which has similar notation, so f sub y. And I can define that as a limit. So what happens now is, it is x that remains fixed, and y changes. So I have f of x naught, y naught plus h, minus f of x naught, y naught, and again divided by h. So now if I were to wander away from x naught, y naught in this direction, I can look at this partial derivative and see, oh, if that partial derivative is positive, a function is increasing in that direction. If it's negative, it's decreasing. So between the two, since this f is a function of just two variables, those two partial derivatives give me a full picture as to how f is behaving. Any questions so far before we take some examples? Because ultimately what you want to be able to do is, just as you did in Cal 1, given a function of however many variables, compute these partial derivatives efficiently. And in Cal 1, you were taught this definition. Maybe you had to carry out a few times, and you found it really annoying. And then your professor would teach you these wonderful differentiation rules, and you'd use that from that point on. And even though it might still be tedious, at least it'd be a whole lot easier than using a definition. Well, we're going to get to that point right now. So I can describe in just a few words how you carry out partial differentiation. Okay, so the idea is you're carrying out one-dimensional or single variable differentiation like you've always done. So this would be able to piggyback off of that knowledge, so hopefully you retained it. With respect to, I'm not going to write out with respect to, it's WRT in this class, get used to it. Respect to one variable, whichever one you need at that time, and you treat all others as a constant. And as you should know from Cal 1, derivative of a constant is going to be 0. So what I'm going to do is I'm going to put out some examples, some simple examples, so that you can get the idea of how this process works. Because how you did derivatives before, that's all going to apply now. You just have to keep in mind how to properly take other variables into account, because you're not necessarily used to that notion of, okay, this variable is what I'm differentiating with respect to, these other variables I'm like ignoring. Okay, so let's look at some two-variable examples. Let's say all right, so x squared plus y cubed. So if I want to treat this as a function of x, so wherever you see y, whatever is being done to y, doesn't matter, that's a constant. So if I think of this only as a function of x, so in fact I could do that. I could define a function g of x as x squared, like if I filled in a specific value for y, like I call it y naught, it'd be something like this. And if I think of this, now what you're seeing is literally a function of one variable, you know how to differentiate that. Well, it's the same idea, it's just that you don't really care which value is plugged in for any of your other variables. So, so take a shot. What is derivative at as a function of x?
2x.
And y is at the end. How come I don't have anything else? Y is treated as a constant. Okay. Whereas if I want the derivative of the same function with respect to y,
3y squared.
3y squared. Now the x squared is treated as a constant. Okay. So if I wanted to know the partial derivative with respect to, let's say, x at a certain point, let's say x is 4 and y is minus 2, then it doesn't matter whether you go ahead and just take this derivative that you just computed, this 2x, and go ahead and plug in only the x value, because the alternative is if I define g of x to be f of x, and then I plug in the specific y value, y equal 2, and that would give me x squared plus minus 2 cubed, so x squared minus 8. And then I can say derivative with respect to x at this point is the same as g prime of the x value. So when you in terms of substituting variables, it doesn't matter whether you do that before differentiation or after. Now, a variable you differentiate with respect to, then it does matter. And the reason why I make this point is so you can see literally what's happening. You are freezing the other variables. They really are constants, whether you substitute a specific value or not. Okay. All right. Do another. Okay, let's make things a little more complicated. Okay, so now we have 3 partial derivatives altogether. And notice how I write my z's, because if I didn't put the slash through them, they'd look like, those really would look like my 2's. So, another thing to get used to. So, if I treat y and z as constants, and I'm only differentiating with respect to x, what would that give me?
E to the z cosine x
Mm-hmm.
plus ln y.
Yeah, because your derivative of x should just be 1, and that natural log of y is sitting as a constant. Just as since z is a constant, e to the z also a constant. So your other variables and any functions of them are treated as constants. Okay, good. What about with respect to y?
X over y.
Yes, because the x is sitting here as a constant. You're differentiating natural log of y, and that gives you 1 over y. So x over y. Okay, and finally, what about df dz? You have e to the z
Times sine x.
times sine x. X is a constant, therefore sine x is also a constant. That's multiplying it. So it hangs around. Constants, whether they're actual constants or maybe they're functions of other variables, when it comes to differentiation, they're like that uncool friend that won't go away, basically. That it just stays there after differentiating. If it's being multiplied, if it's being added, then of course it's 0. So any questions about how these were differentiated? All right. So I'm going to put your knowledge to the test by telling a first, not, I'm sure it's the first you've heard, but I can't promise it's the only, multivariable calculus joke. So if you understand what's going on, you'll laugh or groan. Okay, if you don't get it, then of course it'll be silent, and then you'll give away that you haven't followed this. Okay, so no artificial groans. Okay, so a function e to the x is just walking around like strutting. He thinks he's the coolest of functions because differentiate him, nothing happens. Integrate him, nothing happens. And it's like impervious to those things. So he just thinks he's the it function. But then around the corner comes a constant function 3, bumps into him, and it's like, what's the matter? Like, and it's constant 3, it looks terrified. It's like, there's differentiation operator going around. If he gets me, I'm done. And he just runs off. And e to the x is like, well, what do I have to worry about? I'm e to the x. So he goes around the corner and sees the differentiation operator. And he says, hi, I'm e to the x. And the differentiation operator says, I'm d over dy. Okay. All right. Fine.
Gotcha.
Okay. So if you don't get it, then you need to look at this more closely. So, okay. And like I said, that won't be the last. So just have to put up with it. Okay. Now, just as you, in single variable calculus, also had to deal with second derivatives, or higher order derivatives, those are going to be important to us too, in many cases. And it also plays out much the same way as you just saw for first partial derivatives. Okay. I have an example here. Okay. Maybe a better one. Now, well, first I'll give the definition. But it's really no different than the single variable definition. But the notation is going to take some getting used to. So first, single variable calculus, f double prime at x, also written this way. And you might have found back when you took calculus 1 learned this notation that's rather strange, like the placement of the 2's. But the reason for that is, if you think of differentiation as an operator, like the differentiation operator from the joke, and those generous to call it that, but still, is an operator applied to f. In this case, we're applying it twice, so it's like differentiation operator d dx squared. And that's just taking a derivative of a derivative. Okay. So the same idea applies with functions of several variables. It's just that there's different differentiation operators that you can apply in sequence. So, in the multivariable case, again, we no longer have primes, so we have fxx, and I'll just do a 2-variable case here. So this is an example of a second partial derivative. And the other way it's written is similar to this notation. A partial differentiation operator with respect to x squared applied to f twice. So that would be, you go ahead and take fx, like you've already seen how, and differentiate that with respect to x again. All right, so very similar to single variable differentiation. But now, with more than one independent variable, you have multiple combinations. So we have fxy. So we're differentiating, you can think of it as first with respect to y and then with respect to x. Okay. Now you might think, well, does the order really matter if I differentiate first with respect to y and then x, or then with respect to x first, then y. Because if that was different, that'd be kind of a pain to keep track of. But fortunately, you don't. This is the same as starting with fx and differentiating that with respect to y. So fxy is the same as fyx. So if you're taking a higher order derivative with respect to some sequence of variables, the order in which you carry out the differentiation doesn't matter, at least as long as everything is nice and continuous, which is generally the case. So this is called Clairaut's theorem that says mixed higher order derivatives, not just second, but any order, derivatives are equal. Okay. So if you had to compute all second partial derivatives of a function, that would save you some work. Now in this case, we have two independent variables, x and y. What else do we have as far as possible second partial derivative? What have I left out?
Double y.
Yeah, differentiating with respect to y twice. Similar to differentiating with respect to x twice. Okay, so we have 4 second partial derivatives in total, but only 3 of them are distinct. Okay. And so, being appropriately rigorous, all those second partial derivatives have to be continuous in order to satisfy that property of equality. But again, cases that we'll deal with, that's always going to be the case. Okay.
What do you mean by mixed higher order derivatives?
Something like it's fxy or fyx.
Oh, okay.
Yeah. Well, okay, let's take a look at a slightly more complicated combination. Still second partial derivatives, but with 3 independent variables. So I want to take all possible second partial derivatives of a function of 3 variables, f of x, y, z. So let's see how many distinct second partial derivatives there would be. So what would be some partial derivatives I should have? F what?
xx, xy, z, so on and so forth.
Yeah, so we'll start, I'll put xx right here, and then I'll put xy here, but that's the same as fyx. So these two are equal. Throw out some more. What else we got for combinations? Yeah, so I have fxz, and then fzx, so these two are equal. Yz, okay, so fyz, which is, actually, zy down here equals yz here, so these two are equal. And what are the last two? Y and zz. Okay, so we have, strictly speaking, 9 second partial derivatives. So however many independent variables you have, if I have n independent variables, how many partial derivatives am I going to have? Like in this case, I had 4. Here I have 9. Yes, yeah, so n squared. But that's before you take into account which ones are going to be equal. So I can look at the ones in this lower triangle here, or I could have picked the upper triangle, and those are the distinct ones. So once you have these 3 down here, then you can fill in. The rest. Okay. So the number of second partial derivatives is n squared, but in the case of 2 variables, we only had 3 distinct partial derivatives. Here we have 6. So if n equals, so see what to put here. If n is equal to 1, we only have 1. If it equals 2, you have 3. If it equals 3, we have 6. Does anyone see what the pattern is there? What? Almost. Okay. All right. So it's going to be, it's the sum of all the numbers from 1 to n, which is not n squared minus n, but
I see.
what is it?
You just start with 1. If n is 3, then you just start with 1. You add 3 terms. You got all 3 terms together.
Yeah, 1 plus 2 plus 3.
Yeah, so
Yeah.
if you did 4, it would be 1 plus 2 plus 3 plus 4. And you
Right, but the formula for that is
That's the question.
what?
It's that expression, yeah, the, original.
Is it a summation?
Yeah, but it's a formula for a closed form. And you almost said it. N squared. It's not n squared minus n, but
N squared plus n?
yes. Yeah. N times n plus 1 over 2. Yeah. Okay. Yeah, so for instance, in the case of n equals 3, you'd have 3 times 4 is 12 over 2 is 6. Now, that was probably taught in discrete.
Yes. it
Yeah.
was.
Do you know how that was? Yeah,
You
go ahead.
said it was n squared plus n. That formula is not n squared plus n. That's n squared plus n over 2.
Yeah, but
It's all over 2.
yes, I'm well aware of that. But I was only focusing on the numerator.
Oh, okay.
Yeah.
That's-
Yeah, because the wrong numerator was given first, and I needed to correct that. But yes, all over 2.
Okay.
Yeah. All right, we're good to check that was. All right. Well, actually, this takes me to my next point. Have any of you been told how that formula came about?
Good description.
Okay. Okay, I have just enough time for that. If we're going to keep going with partial derivatives on Wednesday, yeah. Sorry about the swap. I never meant to say that it was n squared plus n, the whole formula. Okay, it was developed by one of the most prolific mathematicians I mentioned earlier, Gauss, who, as a punishment, was told to take all the numbers from 1 to 100 and add them up. So that would take a while. But what he recognized was if you write out all the numbers from 1 to 100, first forwards and then backwards, and we add each column. Yeah, you always get one more than a number of your numbers that you're tasked with adding. So then you can just go ahead and add all of these. So we get 101 times 100, but you've written them out twice, therefore you divide by 2. And so this is your n in this case, n plus 1. So recognizing kind of patterns can lead to a much faster way of doing these problems. That's what all these mathematicians have devoted time to come up with, and that's where, and then these more efficient ways filter down to classes like these. Because at first, for a derivative, the definition comes about from an intuitive understanding of what the derivative is supposed to mean, a rate of change or a slope. But then, after you have that, it's like, well, now what? Trying to apply this in various cases takes too much time. But after doing it with certain kinds of functions, you recognize patterns, you exploit those patterns, and then you come up with something much more efficient. In fact, that's any success I've had in research, for example, is a result of exploiting something like that to find a better way of doing things. Yeah. Okay. Now, all right, I have enough time to at least, I want to do some examples of this. All right. if you have natural log of x squared plus y squared, and we won't have time for all today, but at least we get through the first partial derivatives. So what would be the derivative of that with respect to x?
2x over x squared plus y squared.
Yeah, because by chain rule, you take 1 over that, and then you take a derivative of what's inside, x squared plus y squared, but only with respect to x. So everything you used before, like a chain rule, product rule, quotient rule, all that still applies. You just have to be careful, but you're still carrying out partial differentiation. Okay. Oh, I messed up the example. I only meant to have x plus y squared. So what you just said, based on what I wrote, is correct. But it would just be this. All right, but now for df dy, what you said are similar to that. So you have 2y over x plus y squared. And it's like, why does that not agree with my notes? And that's why. Whereas if I look at, well, df dx, okay. Now, to take fxx, I can just differentiate that with respect to x. So what should that be?
No.
And to make it easier, you can think of this as x plus y squared to minus 1.
Negative 1 over x plus y squared.
Let's square the whole thing squared. And then because we're differentiating with respect to x, you then take the derivative of the inside, but that's still going to be just 1. On the other hand, on the other hand, if I took fyy, and the rest of these will have to wait, so I'm working with that, what would we have to use for that, to carry that out? Quotient rule. Substitutions for integration. So then you'd have x plus y squared times derivative of 2y with respect to y. So that's, and then we'd have 2y x plus y squared with respect to y all over x plus y squared squared. And then these would have to be worked out. So for instance, this would be 2. And this would be what? 2y. Okay. And then you can try to simplify from there. So what we'll do when we pick up on Wednesday is to complete the table that we have all possible second partial derivatives.